So, good morning, all. Yeah, start. Okay, good morning, all of you. It's my pleasure to introduce today's speaker, Dr. Prasanna Kumar VC. Prasanna Kumar VC is working as a professor in Department of Studies and Research in Mathematics, Davangere University. He obtained his UC degree in 1997 from Kuvempu University. Shimoga, Karnataka University, and he obtained his doctorate in 2007, Kuvempu University, Karnataka. Sir, he worked in various positions in various colleges. He started his career in 2004 as assistant professor, Bangalore College of Engineering and Technology, Bangalore. And from 2004 to 2009, he worked in this college as well as SBM Jain College of Engineering, Bangalore, BTL College of Engineering and Technology, Bangalore from 2004 to August 2009. And in September 2009 to April 2019, he worked as assistant professor, Government First Grade College, Koppa, Chikmagalur district, Karnataka. And presently is working as associate professor from 2019 onwards till date in Davangere University, Shimoga. In Davangere University, Shivagangotri, Davangere, Karnataka. So, sir has some achievements, awards he obtained. He is the one among the world's top 2% scientists by money from young scientists for research vision group on science and technology, Government of Karnataka, 2014. And his area of research interest is modeling and computational mathematics, boundary layer theory, numerical methods, Newtonian, non-Newtonian fluids, two-phase fluid flow, nano fluid mechanics. And SAR has some research projects as well. He got UGC sponsored minor research project worth 1,50,000, and he got vision group on science and technology, Government of Karnataka project worth 6 lakh rupees, and he got UGC sponsored major research project worth 12,25,000. He worked this project from 2015 to 2018. A vision group project he worked from March 2014 to 2016, both completed. And UGC sponsored my research project March 2011 to September 2011, he completed. And to his credit, he has 158 research publications in peer-reviewed journals. And he attended a good number of workshops and international, and he presented papers in various international conferences. And to his credit, he published around 10 books in reputed publications. And now, with this brief introduction, I request today's speaker to give a talk on Analytical and numerical methods for solving partial differential equations arising in fluid flow problems. Sir, Prasanna Kumar sir,
Yes, sir. Thank you, sir.
we feel happy to have you here for today's lecture. Please, we request you to deliver a lecture on the said topic, sir.
Sir, thank you. Thank you so much, sir. Is it audible, sir?
Yes, sir, it is audible, sir, quite audible.
Okay. Yes, sir. Very good morning. I hope I am audible. Sir, I am audible. Hello.
Yes, sir. You are audible, sir.
Okay. Thank you so much, sir.
Yeah. So, please continue, sir.
Thank you, sir. So thank you so much for providing me opportunity to discuss on a very interesting topic, analytical and numerical methods for solving fluid flow problems. Earlier, before joining this university, I worked for Jain University in Bangalore, and I was 10 years in various engineering colleges of Bangalore. So I know very much about MSRIT and the standard of education that they are providing. Thank you so much for the opportunity. I am thankful to the organizers. So let me start with effective analytical and numerical methods for solving the fluid flow problems. Now, before starting my actual lecturing, let me explain the difficulties in fluid flow problems. Many are working in fluid dynamics, and even I have taken some examples of solid mechanics, because I am going to explain a one-dimensional DTM. Okay, let me start with. This is what I planned for today's lecturing. Analytical methods, I will explain advantages, and numerical methods advantages, and applications of analytical methods, validation of analytical methods, as well as numerical methods. This is what I planned. Okay. So in the methods for solving fluid flow problems, I will go for analytical, semi-analytical. Particularly semi-analytical I will explain, because many fluid flow problems in various regions don't have closed form solution because of its non-linearity. So I will go for semi-analytical methods like DTM. In DTM, I'll one-dimensional, two-dimensional, and parameterized DTM I'll explain, and also one numerical method, and also I'll explain MATLAB programming, Mathematica, and Maple programming comparison with respect to boundary value problem solver, and difficulties as well as advantages with examples I will explain. Okay, so before starting actual topic, differential transformation method, let me explain the difficulties in solving the problems arising in fluid flow problems, fluid flows. See, as we know, there is no closed form exact solution for the Navier-Stokes equation, which governs the flow problems, and it is a millennium problem also. But because of the approximations, particularly this boundary layer approximations, this could be reduced to easiest way. Some parameters we have deleted, and now we can obtain closed form solution for the few cases. But still, since most of the problems are nonlinear and coupled, it is not an easy to obtain a solution. But many semi-analytical methods are available, like differential transformation method, optical homotopy method, homotopy analysis, homotopy perturbation. Like that, a series solutions methods are also available. But nowadays, because of advancements in the computers, in particular, applied softwares, usage of applied softwares like MATLAB and Mathematica, Maple, we are very much convenient, and we are very much have an advantage of solving these nonlinear problems with inbuilt functions. And I should say it is an ready-made programs like boundary value problem solvers. But it is not easy to get a accurate solution from those, and also validation is not so easy. So in that sense, now actually I am working on solid mechanics problems. Particularly, I am applying a DTM in different ways. I will come later part of my lecturing. How many DTM methods are there? It is a very recent. In 1986, Zio introduced the concept of differential transformation method. It is also a transformation method like Laplace transformation, Fourier transformation, Hankel transformation, wavelet transformation. It is also one of the transformation which uses derivatives. And it is not so old method. It is a, of course, even about 35 years old. It is a new only. In 1986, so introduced it. Indeed, the differential transformation method is based on a Taylor series expansion in a different manner, in which a differential equations is converted into a recurrence relation to get a series solutions in terms of polynomials. Now the anyhow, there is so many difficulties are there in analyzing the series solution, in particularly the convergency, accuracy, and also where to stop, how much terms as sufficient to get it. And for all these, we have a solution, and I have checked with analytical numerical methods also. Payday approximate, I think you have heard of it. Payday approximate is the, I should say, gives more accuracy and more advantages for differential transformation method. Later, I will discuss what is payday approximate and how it is helping and other things. So advantages of differential transformation method. This method can be easily applied, just like Laplace transformation of definition and its inverse Laplace transformation, and Laplace transformation of elementary function we have studied and very much well versed. In same fashion, differential transformation method also can be learned, particularly those who are beginners or those who are working with students, because students can learn this method very easily. But of course, the calculation and computations little difficult, little lengthy, not difficult, little lengthy, because it involves series solutions. But those who are working, guiding students, definitely this will be a very good method. And there are so many advances also in this method. So publication is also quite easy. I will come how this method helpful for me. So this method can be easily applied for different problems like eigenvalue problems, initial value, boundary value problems, and even most of the partial differential equation, integral differential equations, system of differential equations, and delay differential equations, and so many other type of differential equations we can apply. So in comparison with perturbation techniques, so homotopy perturbation method, in comparison with that perturbation method, DTM is independent of small parameters. In perturbation, we use perturbation variable P, but here it is independent. So it is better than a perturbation method. When compared to homotopy analysis method, there we have to calculate H curves, H, and here that problem is not there. Therefore, even it is better compared to HIM. DTM does not need to evaluate an auxiliary function like in HIM. Okay? So it is also easy. DTM allows us to express solution to a nonlinear problems using the Payday approximate with increased reversibility. See, Payday approximate is important. Without Payday, DTM is also like some other methods. But if you able to apply Payday approximate, without using Payday approximate also, we can solve the problems. But if you are able to apply Payday approximate in a very good manner, then definitely this DTM is very good method when compared to homotopy analysis method and homotopy perturbation method. So in all, these are series solution method, and compared to these two methods, this is better. And even many DTM methods are there. So reduced DTM, differential transformation method, parameterized differential. These are the recent advancement. Now types of DTM. Here I discuss one-dimensional DTM, and it is applicable particularly for the solid state or solid mechanics problems, and two-dimensional DTM and its application. And very importantly, recently introduced, very recently, even you can get some 2-3 papers on this alpha parameterized DTM and its applications. And even you can apply 3-dimensional DTM, n-dimensional DTM, but it is little lengthy, and of course computation is little difficult, but I am sure with the help of computer programming it is not much difficult. But much work has not been reported on alpha parameterized DTM, so a lot of opportunities are there for the researchers to use this method effectively in one-dimensional problem. I'm sorry, this is not, this alpha parameterized DTM cannot be applied for higher dimensional problem. So it is an improved version of one-dimensional DTM. So for where there is an one-dimensional, some water pollution, solute transport problems, or even atmospheric modeling, which involves one-dimensional, and solid mechanics problems, effectively we can apply alpha parameterized DTM, which is very effective compared to one-dimensional DTM. As already I mentioned, it is an improved version, it is an advanced version of one-dimensional DTM. Now come to one-dimensional DTM. See, general form of Taylor series. Here we are expressing, it is a Taylor series expansion only, x minus x naught to the power k and k factorial. Here I have introduced that extra d to the power of k of f of x dx to the power of k at x is equal to x naught. This is what I have said. Differential transformation is a Taylor series expansion in a little different manner. Now, the differential transformation fk of a function f of x, just like Laplace transform. I want to compare this differential transformation method with the Laplace transformation method because we are very much familiar in Laplace transformation. See, the differential transformation of a function f of x is given by capital F of k is 1 by k factorial, and this is the thing. And this we can obtain by using again Taylor series expansion only at x is equal to x naught. So now the differential inverse transformation, just like Laplace inverse, we have a differential inverse transformation, that is f of x. If I take inverse Laplace transformation on both sides, I will get f of x like this. Okay, please you remember these two expressions. Next I will use these two in an effective manner. So differential transformation of f of x is this equation, and its inverse is again f of x. These are the properties of one-dimensional DTM. And you observe here, differential transformation of yx will become, I will take yk, k is the parameter I am using here, and g of x will become capital G of k, plus or minus h of x will become capital H of k. And alpha does not make difference. And here the comes, first derivative g dash, it should be k plus 1 into g of k plus 1. Suppose it is second derivative g double dash, then should be k plus 1 into k plus 2 into g of k plus 2. Got my point? Similar third derivative, k plus 1, here it is k plus 1, k plus 2, k plus 3, and so on. Last one, k plus n. If I am taking k plus 3, g of k plus 3. This is for the derivatives. Just like Laplace transformation of addition function, if I multiply it by constant, if it is a derivative like that, it is x to the power m. If it is x to the power of m, you should have, it should be in this form. And if k, that parameter, and m, the power, are equal, then it will be 1. In all other cases, that is 0. And now the product of function, just like fx into gx in Laplace, I am using for f1, f2, so on. Suppose it is only for 2, fx into gx. Then summation r from 0 to k. If only two functions, then f of r, g of k minus r. Got my point? Last one is there, g of k minus r. If it is 3 function, fx, gx, hx, 2 summation will come. One summation I will take from r from 0 to k, another summation I will take l from 0 to r, and so on. This is a simple thing and easily you can follow it. If only one function, there is no summation. Here you see, there is no summation. If it is a product of 2 functions, there will be 1 summation. If it is a product of 3 functions, there will be 2 summations, and so on. Okay. Now, I have applied this differential transformation method in this paper. A hybrid nanofluid flow over a structured cylinder with the impact of homogeneous heterogeneous reactions and Cattaneo-Christowit flux, a series solution and a numerical simulation. I applied my students, actually it is not my paper, it is my students' paper. They applied DTM's method to obtain a series solution, and also we compared, I have obtained solution numerically. If you want to compare my findings, easily you can follow this. If you want to learn basic things, so we have explained very neatly in this paper. So there after similarity transformations, we will get equation 1. Say epsilon 1 constant to eta. Eta is a variable here. Eta into f triple dash. And here f double dash, lambda into f dash, like that. Now I will explain how to apply a DTM transformation to this particular equation. See now epsilon 1 as it is. Now just for this 1 into f triple dash, third derivative. Third derivative means k plus 1, k plus 2, k plus 3, f of k plus 3, as I explained earlier. But here eta, one of the function will appear. Just like product of two function, eta into f triple dash, one summation will come. Did you observe? Here one summation will come. Just because of eta function, so 2 omega constant I kept as it is. Epsilon 1 I kept as it is. Now for eta into f triple dash, all these things will come. All these things means summation r from 0 to k, delta r, k minus r plus 1, because it is a product of two function, it will come. So similarly for next 2 omega into f double dash, next function will come. Similarly for f dash zero. You come to this problem, f of 0 is equal to 0. See here, put f of 0, k is equal to 0, you will get 0. And f of 1, same thing you will get it here. F of 0 is equal to 0, f of 1 is equal to 1. This is a sequence 0, 1, 2. Next, if you require f of 3 like that. But I want only 3 conditions. You see 1, 2, 3. F dash of infinity, we don't know what is the infinity I have to measure. That is what we said, a variable a. I kept it. And this is the challenging one. And now various methods are available to approximate this value a. And this approximate value for a better approximation of a will give us better results. Now, remaining recursive obtained by k is equal to 1, 2, 3, so on. F of 3, f of 4, f of 5, and so on, I can get it. But a few terms are sufficient. And number of terms, as number of terms increases, of course, its efficiency also increases. So, I have expressed in terms of f of eta. This is the thing I am getting. You observe here everywhere capital A. Capital A is the one I required. Substituting these values of all parameters leads to final analytical solution. And this is looks simple. F of eta I got like this. It is a series solution in terms of eta. But how to get this with this value is a matter of payday approximate. If you know a good programming skill, definitely it is not much difficult to obtain capital A and this sequence also. Okay, any difficulties, any doubts here? Any doubts here?
Sir, you please continue, because the participants are attending the session in the YouTube, where they cannot interact with you.
Okay, sir. Fine, sir. Fine,
they are not attending in the Zoom meeting.
Okay, sir. Thank you.
Yeah, you just carry on, sir. Okay. Later at the end, if at all someone poses the doubt, we'll just pose it to you.
Okay, sir. Fine. Thank you.
Yeah.
So, getting this f of eta depends on your how many terms you are getting. Here I have considered only 4 terms. That is sufficient for me. And this final answer, this analytical solution depends on the accuracy of this analytical solution depends on the effective programming with approximate. And we got this, and this is the solution. See, comparison of one-dimensional DTM with other numerical methods. I have compared solid line is DTM and RKF dotted lines. You see, RKF method is a Runge-Kotta-Felberg fourth, fifth order method. Is a very well-known method and very effective as we know it. And particularly solving nonlinear problems, it gives an effective solution. See, this matches exactly. And even later, I will compare it with exact solution also. As I already pointed out, for a very few problems, very few cases, we have an exact solution. This is a velocity. I have find out a velocity. Okay. Now I will go for the two-dimensional DTM. So two-dimensional DTM, here it involves two variables. Then of course, ordinary differentiation is not possible. I have to consider a partial derivatives. So you see, capital Y of K and H. There I have considered only one K, and here it is H. K factorial, K factor, H factorial. So partial derivatives I have considered at X and T. And here I am considering time dependent. One is X variable, another T variable, and at 0, 0. There it was just X is equal to 0. Now differential inverse transformation. For this, if I take inverse, this is a summation H K from 0 to infinity, H from infinite series I will get it. Infinite series. And combining above two equations, we get Y of xt is like this. Properties of two-dimensional DTM. See, it is looks it is little complicated, but no. Once you understood, definitely it is not a difficult one. Now you see original function and its transformation functions. Say of epsilon epsilon 2, C1H, C2H. I will take C1 capital H1, C2 H2. And all the properties are just similar to one-dimensional DTM, except where the product occurs. So here also same. And for partial derivatives, this will be like this. And you see the same thing I applied for second variable. And here product of two function H1, H2, and product of derivative of two function, and so on. And you can observe that the summation exists, and it is an 0 to K and S from 0 to K. And I applied analysis of transient and thermal distribution in convective radial moving rod. And it's a moving rod problem. We applied this two-dimensional differential transformation method with multivariate Pede approximant. We applied a Pede approximant here, and it is also a little different. It is a multivariate because it is more than one variable. And there we will get equation like this: rho theta by tau, partial derivatives of theta with respect to tau, and here capital X, two variable T and X. And these are the initial conditions. Applying DTM to this equation 5 and the boundary condition 6, I will get like this. See, looks lengthy, but computations are lengthy, but procedure is quite easy. And you can observe here, we can get this type of series solution for equation 5. And the boundary conditions are also, boundary conditions will be like this. After transferring, boundary conditions are like this. And solving above equation with the boundary condition, I will get theta 1, 2, theta 1, 3, 2, 2, 2, 3 will be like this. This is after it is a successive approximates. And representing all these terms in the form of Taylor series. We know how to express a Taylor series. I have got this solution. Here, in earlier one-dimensional DTM, I explained how to obtain the velocity. But here it is in temperature, theta of tau x. See, I got this. Even problem is simple. For this simple problem, I have got this much. Okay, substituting the values for all the parameters, lead the final analytical solution. Again, by using Pede approximant, I got beta is equal to like this. Already I mentioned, without applying also you can obtain, but accuracy A matters. Say this one, I have compared again two DTM Pede with the finite difference method. I have compared with the finite difference method. Here also it gives almost exact. Almost it matches with the a finite difference method. So now I come, this is what I want to explain. So this is alpha parameterized deuterium, a new method recently introduced, and very few papers, research papers are available in alpha parameterized deuterium. Alpha parameterized deuterium or alpha PDTM, parameterized deuterium, is the new generalization of the well-known deuterium for the approximate solution of the boundary value problems. Here, alpha belongs to 0, 1, 1, 0 and 1. At alpha is equal to 0 and alpha is equal to 1, this alpha parameterized deuterium reduces to a standard deuterium. Again, the same deuterium, what we discussed in the first stage. The same deuterium we will get. But here it is generalized in between 0 and 1, alpha may take any value. There alpha is equal to 0 and alpha is equal to 1, it becomes a traditional deuterium method. Okay, so this is the definition, this is the sequence, d alpha. Just like those who are working in fractional calculus will know this type of equations, just like in fractional calculus. So this is called a alpha parameterized differential transformation of f. This is a differential transformation of function f. Then the series solution is given by like this. It's called a alpha parameterized differential inverse transformation. Now comparison of two-dimensional DTM with other numerical methods. So here also I have compared two-dimensional DTM. Sorry, alpha DTM. So application of alpha parameterized DTM I'll explain. Now consider a following ODE. For simple problem I'll explain. Y double dash 3y dash is equal to 0. As already I have mentioned, alpha parameterized DTM is the improved version of one-dimensional DTM. We can apply only for presently we can apply only for an ordinary differential equation. It is a one-dimensional. So with boundary condition, simple examples I consider for the purpose of explaining. Here x belongs to -1, 0. Now applying alpha parameterized DTM to equation 10. See, I'm applying for y double dash 3y at alpha and k is the parameter. So y double dash k plus 1, k plus 2, same thing. There was no alpha in one-dimensional DTM. Here alpha will come. Similarly, 3 into y, 3 into differential transformation of y alpha, k is equal to 0. And -1 and 0. Here x belongs to -1, 0. Therefore, at y alpha of -1 and y dash of alpha of 0. I have considered like this. Oh, sorry, here I am applying boundary condition. Y alpha of -1 and y dash of 0. And this is 1 and this is 0 and this is 1. Y of -1 is equal to 0 gives this equation. And y dash of 0 is equal to 1 gives this equation. Equation 13 is after applying alpha parameterized DTM to the boundary conditions 11. Now, let us assume dy alpha is equal to a, dy alpha at 1 is equal to b, 0 and 1. At 0 and 1. Then substituting in the recursive relation 12, I got like this. This is the equation which we will get. And the recursive relation is represented by this equation. Okay, and you observe it for one-dimensional DTM and alpha parameterized DTM, alpha is extra and all the terms are same. And A and B values are evaluated from the boundary condition. Now I got two values, A and B, and this should be evaluated with the this A and B should be evaluated with using the boundary condition. This by using this boundary condition, I can evaluate A and B, and we can get the final solution. And you see, I have solved the same problem with one-dimensional DTM and alpha DTM. There is no much difference. But you can ask a question. Then, if both are same y alpha, the only thing is here it is an improved version. For this particular problem, it may looks both are same, but in higher problems, higher complex problems, definitely alpha PDTM gives a more accurate result. And I already have mentioned alpha PDTM will be is equal to DTM when I take alpha is equal to 0 or 1. Next one is spectral. This is what one analytical method I have explained. Now I'll go for the numerical methods. So spectral collocation method, and many of you already have a good knowledge about the Galerkin method and pseudo spectral method. These are one of the spectral method, and I am using collocation method. So few problems we have solved, research problems with spectral collocation method. Those who are having good computational, means writing a computer program skills, definitely will have a good advantage of this. Advantages of spectral collocation method. In the field of numerical simulation, spectral methods have been shown to have a very fast rate of convergence. Spectral method. That's why Galerkin method is very famous, and very large converging speed when compared to most commonly used numerical methods. FEM, finite element method, finite volume methods provide linear convergence, whereas these spectral methods provide exponential convergence. It is faster than these two. The main advantages of spectral method is that accuracy when dealing with a small number of unknowns, particularly when there is a small number of unknowns. It may not be so effective when we are considering a coupled equation, but when there are very few variables are there, very small number of unknowns are there, then definitely this method is more advantageous. This spectral Chebyshev collocation method, we applied this method, and it's quite simple. Programming also quite simple. This is a non-periodic special domain. And application of spectral collocation method. Consider this problem. This is again a fin problem with boundary condition. So after applying this, the equation can be rearranged. Just I have rearranged this equation. I did multiplication, and after this I am getting this equation. So now I will apply according to spectral collocation theory on collocation points can be approximated by Lagrange interpolation polynomial, such as the Lagrange interpolation polynomial. The matrix form of a spectral discretized algebraic equation can be expressed like this, and after that I will get FKL and HK are defined this, and so these are all inbuilt functions. Easily you can understand these things. Only point is a programming side, how to do effective programming. See, so this is the equation I'm going to apply spectral collocation method. You can observe here, after applying, you see n+1, x maximum, x minimum, it's all comes from this FKL and HK. Okay. Comparison of spectral collocation method with other methods. I have comparison spectral collocation method with least square method and RK again Runge-Kutta-Fehlberg method, and all satisfies, all supports this method. This is even though it is one of the old method, but it is having its own advantage. But I tell you that this method is more effective when we have very small number of unknowns. Otherwise, it is little difficult, and we cannot depend on its solution. Okay. So now, up to this method, we used software. I used inbuilt programming softwares like MATLAB and Maple. We are using Maple exclusively, and even MATLAB programming also we are doing. Now, there is a doubt always which programming is better, and how to do a programming. And I will explain BUP 4C, BUP 5C, boundary value problem 4C, boundary value problem 5C. This word you must be heard in MATLAB programming. And also a boundary value problem ND solver, D solver. We can heard this word with respect to Mathematica and Maple. Those things I will explain, and I will compare which one is best. Say MATLAB. So MATLAB, we have two functions, BUP4C and BUP5C. Boundary value problem solver 5C, boundary value problem solver 4C. Program is little different. Minimum changes are there, but there is a quite difference in these two. BUP5C always gives better solution than BUP4C, but it has its own limitations. I'll explain it. BUP4C. The maximum error is more compared to 5C. 5C, and compared to BP 5C, this 4C is having maximum error. ODE function is less. Calls to ODE function. Any of this method, BP4C and boundary value problem, we have convert PD to ODE and we have to solve. But calls to the ODE function is less. Calls to ODE function is more. Calling this function is more in BP5C. And calls to boundary condition function is less. Boundary condition is more. And calls means number of requirement for ODE and as well as boundary condition is more in 5C and compared to 4C. In BP4C, the solution obtained with a smaller number of mesh points. And in BP5C, we use more number of mesh points. Mathematica. So, the term Mathematica means subjects of instructions, which helps us to solve particular problem in the base of mathematics and used to perform complex queries. We are using this Mathematica also. Mathematica is most known for its symbolic computing, although it is much more than symbolic computing, but it is mostly known for symbolic computing. Definitely, it is not just a symbolic, it is more than that. And so Maple, and we use Maple programming also. Maple started off a symbolic solver in the early 80s. And some features of Maple, it makes matrix manipulation tools along with spare arrays. And generally speaking, MATLAB is the best for numerical computation. Maple is the best for producing various type of plots and graphs. And Mathematica is best for function analysis. Means if you are finding analytical solution, and I hope you know that for many problems, we can get analytical solution easily using these softwares. But flats and graphs, Maple is the best, and MATLAB for all numerical computations, and Mathematica best for the functions analysis. So now I'll provide an example for a MATLAB programming. Okay, I will take one example of Chakrabarti and Gupta, and they obtained the exact solution. This reference. Okay, this is a very old article, 1979 article, Quarterly Applied Mathematics Journal article. And there you see f third derivative minus f dash square, f double dash. This is a very famous problem with the required number of boundary conditions. Okay, in MATLAB 4C or 5C, we do programming like this. You know, f is equal to y of 1, f dash is equal to y of 2, f triple dash is y of 3, y of 1, y of 2, y of 3. We are converting in ordinaries. See, y dash of 1, y dash of 2, y dash of 3. These are higher order ordinary differential equation converted to first order ordinary differential equation with even boundary conditions also. So this will be programmed later. But in a Maple, directly we can solve ODE, boundary value problem solve, which mid-range program like that also we can write. See, in Mathematica we use NDSolve. In Maple we use DSolve. See, plots comparing various functions of MATLAB and Maple. So this is BP4C. The same problem I am solving with BP4C, BP5C, and also Maple. You observe here, there is no change in the interpretation, and very less. Here also decreasing, here also decreasing, and here also it is actually decreasing. I have not mentioned. It is decreasing. F dash of eta is decreases for the improving value of m is equal to 1. It is a magnetic effect I am considering. But you observe carefully the diagram. Even though eta infinity I have taken 3, this is a eta infinity value 3. Eta infinity is at 3. Eta infinity is at 3. You observe there is an first, when m is equal to 1, there is no problem here. But here there is a problem. Even if eta infinity I have taken 2.5, it is sufficient here. But here it is not sufficient. The program will not converge. That's why I said many calls to ODE. The disadvantage of BP5C is we should give more calls to ODE. And in Maple, you see, even compared to BP4C 2.5, Maple is also 2.5 sufficient. Eta infinity no need to worry. But in BP5C, while programming, we should be very careful about the convergence criteria. In both, we should have better convergence criteria is very important in these two aspects. And same thing, I applied temperatures also. You see here it is easily you can identify. Of course, everywhere 1.5. As I have mentioned, there is no change in that. In behavior wise, there is no change. And that to BP4C and BP5C, it is a matter for next I will numerical I will explain. There you can see it very easily. So here MATLAB and Maple programming I have explained. You see, and here I plotted for both BP5C and BP4C. Very minute change, very minute change. Did you observe any change here? No, it's very minute. And you see the nature of graphs, both are same. See, first graph I solved with MATLAB, second with Maple. But first graph again I solved with BP5C and 4C, and there is no much difference. But in both the softwares, but BP4C and 5C, there is a little change. But in BP5C, even though program is little lengthy, but I suggest this program. Now come to the numerical values. So if come to the numerical values, this same Chakrabarty and Gupta, M value at 5 and 10, it is an exact solution. You obtained exact solution. 0.9154, 8837. You see BP4C, 9154, 9154, 9154. No changes with 4C, 5C, Maple programming. But only the matter is next digits. See, 218, 223, here 222. No resembles, all are not equal. So we have to choose a particular programming. But I have verified BP5C gives better accuracy than BP4C, even at the fifth digit. Here 1, 2, 3, 4, C, fifth 5. 1, 2, 3, 4, 5. 5 digits are same. Next digit is the matters. But if you are concentrating on 5 digit accuracy or 6 digit accuracy, then there is no question of choosing a programming. But you are going to get a more accuracy, choose BP5C. So thank you so much for your listening. Now I want questions from your side so that I can discuss more on that.
Yes, sir. Thank you very much, sir. This session was not an interactive session.
Okay.
We thought that it may disturb the speaker, and so we live streamed it in the YouTube.
Okay, sir. Okay, sir.
We may get some questions later on.
Yes, sir. Yes,
but not instantaneously now.
Okay, sir. Okay, sir.
As and when we get it, we'll just ask you for that and we'll clarify with that.
Okay, sir. Okay, sir.
And we are very much thankful to you, sir, for sparing your time.
Yes, sir. I need actually my collaborator Soumya is working, and even Vijay is my friend.
Oh, okay.
Vijay is my friend. I will come once and we will discuss, because my students they are doing very good programming in MATLAB.
Okay.
And I want to share those ideas with your research team.
Very much welcome, sir. We are very much thankful to you for that as well.
Yes, because once we are all thorough with programming,
yes, sir,
we can develop a research group.
Sure, sir. We'll collaborate and we'll have an association.
So may I know who is speaking?
I'm Govindraj.
Govindraj, I think we met many times.
Oh, is it?
Yes. I worked for Jain University.
Okay.
10 years I worked in Bangalore.
Okay,
fine, sir.
Sure, sir. Thank you for elaborately explaining that spectral collocation method and the differential transform method and MATLAB, Maple, the comparisons, everything.
Yes.
The entire talk was really good, and we again thank you very much for it.
Yes. Thank you, sir. Thank you.
Yeah, we will have a meet again later.
Okay, sir. Sure, sir. Sure.
With this, we close this session now.
Okay.
We'll continue the next session at 1:45.
Okay, sir. Thank you.
Yeah. Thank you, sir. Thank you very much.